All right, that is all I want to talk about in terms of sources of EMF. And so now we're going to get into complex DC circuits proper here with what we call Kirchhoff's rules. So the problem we're going to look at here in a little bit is we want to find the current going through all three of these lovely resistors. So the question you might ask yourself is, how do I recognize in this case that I need to do something with Kirchhoff's rules and I just can't like start combining resistors in parallel series? And the big evidence usually is that you have more than one EMF source in your circuit. And so when you have more than one EMF source, in this case 2 batteries, so simple treatment like we've been doing with resistors in series and parallel is not going to work. And so we go to Kirchhoff's rules. Let's take a look at Kirchhoff's rules. So usually we look at Kirchhoff's rules, we kind of colloquially name them the junction rule and the loop rule. So in this case, your junction rule just says that any current flowing into a junction will equal the current flowing out of a junction. So if we pick any junction here, and I'm just going to choose this junction right here. So then in these 3 pathways, 1 or 2 of them will have current flowing in and the other remaining will have current flowing out. Well, any current flowing in equals any current flowing out. That is Kirchhoff's junction rule. So nothing too crazy there. We can also look at the loop rule, and the loop rule says if you take any loop in a circuit, all the potential increases will be perfectly balanced by all the potential decreases. That way overall the change of potential in one complete loop is always 0. So in this case, every time you go from negative to positive, so going through an EMF source here, a battery, you're going to have an increase in potential. But every time you typically go across a resistor, you'd have a decrease in potential. Cool, and this works for any loop. You can take either of these small loops, or you could take the big loop all the way around. And so in this case, your loop rule will actually allow you to create 3 equations. Your junction rule is going to end up allowing you to only create 1 equation. And so if we see how this actually applies, let's take a gander here. So we got to define some things. We've got to define our currents ourselves. So in this case, if I look at, I usually start from my largest battery. My largest battery is this guy. And so in this case, which direction is he going to want to try and cause current or conventional current to flow? Yeah, this way. And so everywhere on this pathway until I hit a junction, I'm going to call that I1. Cool. So that's current number 1. Flows into that junction. Cool. Then I go to my other source of EMF here. So, and I see him. In this case, he wants to cause current to flow this direction. And so I'm going to call this entire pathway I2. And so I have both of these flowing into this junction, and so then flowing out of the junction would be I3. And our junction rule essentially here is only going to tell us that what flows in flows out. So I1 plus I2 will equal I3. Everybody cool with that? So anything flowing in flows out. One thing to note, when you go and solve for I1, I2, and I3, now I looked at the EMFs here and chose these in some kind of logical sense of which way they might flow, but it's not always so easy to tell, and we may have it wrong here in this case as well. If you solve for a current and the current comes out negative, it just means that whatever direction you chose for it to flow at the beginning, you chose the wrong direction. So if at the end I solve for I3 and I3 comes out as like negative 2 amps, that would mean 2 amps is flowing this way through I3. We'll also find out that as you're going through resistors, you typically have a voltage drop. Now, if you go through a resistor in the direction that the current is flowing, the way you've designed it, that's going to be a voltage drop. But if by chance you happen to go the opposite direction, we'd actually look at it as a voltage increase going through that resistor. So also, if you go across a battery here from negative to positive, that's a voltage increase. But if we went the other way, we'd look at that as a voltage decrease. We'll see this where this becomes relevant in some of our loops here. So let's look at how we'd set up some loop rules here. So let's just call the first loop the loop on the left. So in this case, I'm going to go around counterclockwise. I personally like starting from the battery itself. So I'm going to start right here and go around clockwise. And so in this case, in loop number 1, I've got a 10 volt increase. In loop number 1, what's the next circuit element we hit as we go around starting with that battery? 6 ohm resistor. What current is flowing through the 6 ohm resistor? 1, 2, or 3? 3. So we got I3 flowing through there. What is the formula according to Ohm's law for the voltage drop across a resistor? Delta V equals IR. And so in this case, it's I3, and the resistance is 6 ohms. And so in this case, we'd have a voltage drop of minus 6 ohms times I3. And I'm going to leave the units out of here just to not clutter these equations up too much. Cool. We defined I3 as going this direction. And so since we're going across that resistor in the direction as the current we defined, then it'll be a voltage drop. What's the next circuit element we encounter here? Yeah, the 4 ohms. And what current flows through the 4 ohm resistor? I2. I2. And does it flow in the direction we defined it? Or on the direction of the loop we're going? Yeah. And so we're going to have another voltage drop of 4 ohms times I2.
So if it's going in the flow, you subtract it from the battery?
Correct. It'll be a voltage drop going that direction. Cool. And all this adds up to 0. We're back to the battery at that point. Cool. What I often like to do is I like to get all the terms containing i's on the left-hand side of the equation and the volts on the right-hand side of the equation. And so if you notice, this might reduce down to, and I like to put them in order, like 1, 2, 3 with the i's. So we'll have negative 4 I2 minus 6 I3 equals negative 10 volts. If you notice, though, every term is negative. And so what might I be tempted to do here? I'm just going to make them all positive. Multiply by the negative 1 all the way through. Cool. Cool. And that's Kirchhoff's loop rule for what we've got called loop number 1 there. So if we do the other small loop next, and which way might current be going through in this other loop here? So, and again, I defined it going around this way clockwise. So loop number 2 here, we'll take it clockwise instead. And again, I like to start at the battery. So that's loop number 1. Loop number 2, start with the 12 volts. And is it a 12 volt increase or decrease? Increase, going from minus to plus. What's next element we come across? 8 ohm resistor, what current flows through it? I1, is it flowing in the direction that we're going in the loop?
Yes.
That's fine, yeah. So we're gonna have a voltage drop of? Good, what's the next element we hit? Yeah, I3 flowing through the 6 ohm resistor in the way that it's defined. So again, it's another voltage drop, so minus 6 I3. Anything else? No, that's the whole loop, 0. And so if we do the same thing I did earlier, we'll have negative 8 I1 minus 6 I3 equals negative 12 volts. And again, what am I probably about to do? Yeah, just make them all positive. Change all their signs. Great. And that's what loop 2 results down to. So, and then finally, we can do the big loop. And that's all around the outside here. Do you want to do it clockwise or counterclockwise? It's kind of arbitrary. It's our choice. Clockwise it is. So, cool. We'll go clockwise all the way around. We'll call that big loop loop number 3. And in this case, I'm going to start at the 12 volt battery in the direction that we're going clockwise. Is that a voltage increase or a voltage decrease?
Decrease.
Ooh, going from minus to plus, little to big, so that's increase. So in this case, 12 volt increase. What's the next circuit element we cross? 8 ohm resistor. What current's flowing through it? I1 in the direction we defined. So it's a voltage drop. Awesome. So minus 8 I1. What's next?
6 ohm resistor.
Ooh, we never hit that.
10 volts.
Ooh, yeah, 10 volts. And is it an increase or decrease the way we're going?
Decrease.
With a decrease. We got to subtract 10 volts.
So when you go to a junction, why don't you?
Well, again, so we did the little loops. Now we're doing the big loop around the outside.
You're not worried about this.
Yep. Any single loop, though, Kirchhoff's loop rule says that the overall change of potential has to be 0. Whether you choose a little loop or the entire big loop, it does not matter.
But for the third loop, how is it -8? Because it's going the same direction as the I.
Right, and that's when you go through a resistor in the direction the current is defined, that's when it's a voltage drop.
Okay.
Cool. So, all right, so now we're going to lose the 10 volts here. And then what current's flowing through our 4 ohm resistor? I2, but in the direction we defined? No. So instead of a voltage drop, we'll treat it as a voltage increase. So in this case, instead of minus 4 I2, it'll be plus. 4I2. And anything else? Nope, so that all adds up to 0. So in this case, what's 12 volts minus 10 volts? 2 volts, and I'll move it to the other side, just like we've been doing, and make that negative 2 volts. And then I've got negative 8I1 plus 4I2. And I'm going to actually change the sign on all these as well. Same kind of way I've been doing. So this is going to be positive 2 volts. This is going to be positive 8I1, but what do I need to make sure I do here? Make that negative 4I2. Great. And that's loop rule number 3 here. It's my convention. I do usually change it all the time and stuff like that, but yeah, change to make the voltage positive is one way to look at it, but it wouldn't have worked out that way if we'd gone around the other way. Right. So it's kind of personal preference and stuff like that. Cool. The reason I set it up this way is we now have a system of equations. How many variables do we have in this equation? We got 3, and so we need 3 independent equations to be able to solve for those 3 variables, I1, I2, and I3. So, and your loop rule and your junction rule is designed to get you there. So one way to solve a system of equations when you have more than just simply x and y, substitution is not going to be the fastest thing in the world. So anybody know of a whole form of mathematics that's designed at solving systems of equations? Linear algebra. That's the whole point. When you have more than just x and y, x, y, and z, or 4 variables, or 5 variables, or 6 variables. When you start having more than 2 variables, that's all linear algebra. That's all designed to solve for this. So, and you can actually program this into your calculator to solve it very quickly with a matrix and stuff like that. So I'm not going to cover that. I'm going to make a quick video on that someday. But in this case, we're just going to use substitution and work our way through this. If you started having more than 3 variables, though, substitution would take forever. So let's look at this for a minute. So which variables are in my junction rule? All 3, I1, I2, and I3. Which one are in the first loop? I2 and I3. Second loop? I1 and I3. In the third loop? I1 and I2. Are there any 2 equations I can combine that have the same 2 variables so I can, substitute or do linear combination or something? No. So I'm going to have to do this more than once. All right. So a couple things we can do. I know I1 plus I2 equals I3, which would make it really easy to substitute an equation that has I3 into it and substitute I1 and I2 into it. So in this case, which equation has I1 and I2 in it? Good. Is there an equation that has either just I1 and I3 or just I2 and I3? 2 and 3, or here 1 and 3. Because if I go and substitute either here or here for I3 as I1 plus I2, then I would now have an additional equation that only has I1 and I2 in it, just like our third loop rule, and I'll be able to combine those in one way, shape, or form to solve for those 2 variables. So I'm just going to pick the first one that we have here, and I'm going to substitute in I1 plus I2 for I3 right there. So and I'm just going to start right back here at the top. That's going to turn our loop rule there into 4I2 plus 6 times, and what's I3 equal to again?
1, I1 plus I2.
Cool, and that's still equal to what? Awesome. Cool, and if we expand this out, that would be 4I2 plus 6I1 plus 6I2 equals 10 volts. We can combine the I2 terms. So we get 6I1 plus 10I2 equals 10 volts. Great. Now if I combine that with what we already have from number 3 here, in fact, I'm going to rewrite number 3 right below this, and I've got I1 minus 4I2 equals positive 2 volts. So we got a couple different things we can do. I can solve either one of these for I1 or I2 and substitute it into the other equation. My personal favorite is going the route of using what's called linear combination and just causing one of these variables to cancel. It's probably easiest to do this with whichever variables have opposite signs to begin with, if there are any. Which variables already have opposite signs? I2. And so in this case, I want them both to equal the same number. So in this case, I could do that. I could multiply both of these by the same thing. But in looking at this, I can see I can actually get there in one step if I want to. How do I turn negative 4 into negative 10? So, yeah, multiply by 10 fourths, which is the same thing as 5 halves. So if we do that, what's 5 halves times 8? Cool. And then times 4 is negative 10I2. And then times 2 would be 5 volts. And then I'm simply going to add these two equations together. And when I add them together, what cancels? The I2s. And what will I be left with here?
26 I1 equals 15 volts.
And here's where I need you to pull out your calculator. Somebody get me a value of I1? 0.577 what?
Is that coulombs? It's coulombs per second.
Coulombs per second, which is the same thing as an amp. Awesome. Cool. There's I1. That's one of our answers. If you notice, the question was how much current is flowing through each of the resistors? And we just figured out that through the 8 ohm resistor, it's 0.577 amps. Okay. Now that I have I1, now what do I do?
You plug it into the one that has a I2.
Yeah.
I1 and I2.
Cool. So this one's got both I1 and I2. So I'll just take and plug in I1 right there. And we'll get 8 times 0.577 amps minus 4 I2 equals 2 volts. Now let's see what this gives us for I2. Cool, 0.654 amps. So again, now we've answered another question. So I2 here is defined as the current flowing through the 4 ohm resistor. Great. And so if you look now, if I've got from this side, I've got 0.577 amps flowing into that junction. From this side, I've got 0.654 amps flowing into it. How much must be flowing out?
1.23.
Yeah, I'm just going to plug those into my junction rule to get I3. So in this case, 0.577 amps plus 0.654 amps. What did you get for that, sorry? 1.23 amps, and there's our I3. So did all of our currents come out positive? They did. What does that mean?
They're running in the direction we defined.
Yeah, they're all flow in the directions that we defined. Fantastic.
So if you get a negative current, can you just use that same answer but make it positive?
So, and say it flows the opposite way, yeah. So again, if you get a negative current, like let's say I3 came out to negative 1.23 amps, it would just mean that 1.23 amps is flowing this
So you
way.
have to change all your equations though?
No, it doesn't change any of your equations. All your equations are totally still valid. Cool. So, kind of a long question. So, how much time do you have to take your exams? 50 minutes. If this is one of 12 questions, you're screwed. So, how do I make this easier on you on a test if I realize that you're in a time crunch?
So you don't ask this many variables.
No, I just be nice to you and I tell you, here's your problem. I want to know how much current's flowing through a couple of the resistors. And by the way, I'm going to tell you up front that through the 8 ohm resistor, 0.577 amps is already flowing through there. Notice if I give you one of the variables already, it makes it way easier. You still got to set up your loop and junction rules. And so I'm still testing to see if you know how to set up the equations properly. But if I give you one of the currents, I've just eliminated one of the variables. It makes solving this way faster.
You wouldn't have to do the whole outside loop, you could just focus on the 2 inside.
Correct. We could have potentially just, actually, I think we still would have had to do the outside loop. So to get there, because one of the inside loops doesn't even have I1 in it. So, but we could have ignored this loop completely and just focused on these two or something like that. And yeah, cool. Questions?
So if you were to set up a matrix, could you just do the first 3 and then do 4 of them and then do 0 to 0? Like, what was that called? Do you know
So
what
yeah, so the matrix algebra, if you set up the matrix, like if you look at their first loop, what you've got, and again, focus right here. Right here, I wrote these in this form for a reason, and then right here. If you focus on those, we'll come back to the junction rule in a second, but here, so if you set up your matrix, your first is going to be no I1s, then 4 I2s, then 6 I3s equals 10 volts. That's essentially what your first equation would look like in a matrix. Your second one here would be 8 I1s, 0 I2s, 6 I3s equals 12 volts. Your next one here would be 8 I1s, negative 4 I2s, 0 and 2. And then what about your junction rule? What would that be?
1, 1, negative 1, 0.
Awesome.
And then would you do 0, 0, 0, 1, and then 0, 1, 0, 0? And
So,
you know what I'm talking about?
right, so you want to get this into what's called reduced row echelon form, and your calculator's a function for this. So once you put this in here, you just want to do this operation on this matrix, and it's going to turn it into 1, 0, 0 answer, 0, 1, 0 answer, 0, 0, 1 answer kind of a thing, and you'll know exactly what your first, second, and third variables are equal to.